All right, welcome back, everyone. This is Fluid Mechanics review for exam one. So I wanted to get this out yesterday, but I'm producing it today. And hopefully it'll be helpful for you to prepare for Wednesday's exam. If you want to come early and start early, I'm here usually around 7:30. So um, feel free to do that. No problem. It's not that long. I don't think time will be an issue, but I think it's 5 problems. I just made it not long ago, so now is a good time to do the review because everything is fresh in my head that you have to think about. So, all right, I'm gonna flip you over and use a pad of paper. All right, hopefully it focuses for us. There we go. All right, so starting off with fluid properties. All right. So know your fluid properties and kind of what we did with them. This was the density lab, for example. So we have specific weight. Remember that that is pounds because of the weight. It's pounds per foot cubed or pounds per inch cubed or weight per volume, right? Weight per volume. So be careful on the exam to pay close attention to the units that I ask for, whether that is, inches cubed, feet cubed, pounds, newtons, meters, whatever's being asked for, make sure you give it to me in that same unit. So we also did density. So remember that density is mass. So for this unit, it's going to be a slug per foot cubed. And then in the metric systems, it's often kilograms or grams. All right. So those are the big ones. We talked about viscosity. So you could look that up and remind yourself of what viscosity is. But these are fluid properties that we spent a little bit of time working on. Then we went into pressure and calculating pressure. So the specific weight of the fluid times a Z, right? So pressure was the specific weight of a fluid times the Z depth. So kind of refresh yourself on how pressure works, what angle it works at. So remember that pressure underwater acts in all directions, perpendicular to surfaces, right? All the way around. So kind of refresh your memory on how pressure works and how to calculate a pressure. Also refresh your memory on elevations. Because sometimes the depth will come to you in elevations, like 0 could be sea level. That's very common, right? So then something else happens at 10 feet, something else happens at 40 feet, and then, the top of the water is at 60 feet. So you just have to use these elevations to figure out like how much the depth is, Z, right? That would be 20 feet. All right. So remind yourself on how all that works and calculating pressures. And again, the pressures that we primarily use are PSI and PSF. Those are the common US pressures that we worked with. Okay. So pounds per square inch could be newtons. So newtons per millimeters squared, right? That's a pressure. And maybe remind yourself of what a Pascal is. We haven't used Pascals a lot, but we will use Pascals soon. So what is that? A Newton per meter squared, right? Look that up because there's a few different ones for Pascals. Again, we haven't used it a lot, will not be emphasized on the test. After pressure, we did hydrostatic force. So remember how to calculate hydrostatic force. If we have a reservoir of water, and at the bottom maybe there's a hatch. I'll just draw it in a square hatch, and we want to know what the hydrostatic force is on that. How do we calculate that? We have to draw the load curve. Whatever you're trying to calculate, you have to draw the load curve. And that is a volume of load that is going to act over a surface. So a horizontal surface at the bottom is probably the easiest. How do we know this load right here? It's the pressure at that surface, right? So we'd have to calculate the pressure. And then we'd have to calculate this area and this volume, right? This area times this pressure gives you the hydrostatic force on an underwater surface. So refresh your memory on that. We did vertical surfaces. We did even sloped surfaces. So we did a few of them. And this worked itself into buoyancy. So remind yourself, I think that's probably a bad spelling. Sorry about that. Buoyancy. Remind yourself how to calculate a buoyancy, whether something floats or not. There's a few different ways to do it, right? If we know the weight of the object and we know the volume of the object, we can calculate the weight per volume, right? That essentially is the specific weight of this object. Now, we can also calculate, based on this volume, the volume that is water displaced or fluid displaced and its weight, and we can compare the two to see if something floats or not. So this is the specific weight of the object. Then we would calculate the specific weight of the volume of water displaced, right? So that's going to be a volume, and then it would be times the specific weight of water. And then we can compare these two. If the object specific weight is greater than the specific weight of the water displaced, then it's going to sink, right? So if this displaces more weight in water than what it has, then it's going to sink. If it displaces less weight in water than what it has in weight, then it's going to float, right? So then if it floats, it has a float line. So that means that this area displaced is the same as the weight coming down. So refresh your memory on that. There'll be definitely some buoyancy questions on the test, right? Remember how you calculated water line. So if we have an object, I'm just going to make this some very simple numbers. It's going to be 6 inches by 6 inches. Oops, come on, pencil. There we go. By 10 inches. All right, and we're going to say it weighs 7 pounds. So that's the weight coming down. 6 inches by 6 inches by 10 inches, okay? And so the first calculation is just whether it is going to float or not. So that's easy to do. We just get the volume of it. 6 times 6 is 36, times 10 is 360 inches cubed, right? To get that into feet cubed, because I know my water is 62.47 pounds per feet cubed, right? So if I get this into feet cubed, that's going to help me. So I take my 360 1.25. This equals 1.25 feet cubed, right? And it only weighs 7 pounds. So I can tell you right now, it's going to float. Like, if the whole thing went into water, it would displace so much, way more than 7 pounds, right? So since this is such a small number, 7 pounds, and we're already over a cubic foot, which is 62.47 pounds, this thing weighs way less than the amount of water it would displace. This thing definitely floats, no question. Okay. So now, how do we know the float line? Well, it weighs 7 pounds. So we can set the amount of water displaced, which we don't know, right? This becomes Z, right? So we don't know how much water gets displaced, but we know it's going to be equal to the weight of 7 pounds. So I need to just write the formula for water displacement, which is going to be the volume 6 times 10, 6 times 10 times Z, which is the water line, right? Times the specific weight of water, 62.47 pounds per foot cube. Now, this is inches, this is inches, this is inches. I want to know inches for my water line. I got to get rid of this. So I need 1 foot cubed is 12 to the third inches to the third, right? And that's the amount, that's the weight displaced, right? This weight down here displaced, and I want it to be equal to 7 pounds. So you put the weight in, and it's going to give you that water line, right? That makes this equation equal 7 times, or 7 pounds equals 7 pounds. These cross, all of these inches cross, and we're left with pounds. Okay? So I can calculate that fairly quickly, I think. So I'm dividing the 7 by 6 and 10 and 62.47. Then I have to multiply by 12 to the third. So I gotta go. It looks like 3.227. So Z equals 3.227 inches. So it's further up than I thought, right? It's almost halfway up the 6 inches. So that's how you do it, water line. All right, so we've done buoyancy, we've done waterline work, we've done hydrostatic pressure, and we have done regular pressure and properties of fluids. So that should do it. That will get you 100% prepared for the exam. It's open book. And yeah, we'll see you all in the morning.